Hi everyone, welcome to this course. In this tutorial, we're going to talk about slightly deeper about three main components which frequently appear when doing Arduino projects. Those hardware are Arduino, of course, LED, and resistor. As you may know, there are a variety types of Arduino, such as Arduino Uno, Arduino Nano, Arduino Mega, Arduino Leonardo, Arduino Nintendo, etc. etc. But in these courses, we're gonna to focus on Arduino Uno. But you may know that it has too many things in common with others. As you may know, Arduino is an open source platform used for building electronics projects. Arduino consists of both a physical programmable circuit board, often referred to as a microcontroller, and a piece of software or IDE integrated development environment that runs on your computer, used to write and upload computer code to a physical board. The Arduino platform has become quite popular with people just starting out with electronics and for good reasons. Unlike most previous programmable circuits boards, the Arduino does not need a separate piece of hardware, which is also called a programmer, in order to load a new code onto the board. You can simply use a USB cable. Additionally, the Arduino IDE uses a simplified version of C++, making it easier to learn to program. Arduino provides a standard form factor that breaks out the functions of a microcontroller into a more accessible package. So, as I promised you, we go to deeper Arduino. And there are many varieties of Arduino boards that can be used for different purposes. Some boards look a bit different from the one below, but most Arduinos have the majority of these components in common. The power, uh, the power USB or power jack. The USB, which is level one, and the power jack level two. Uh, so you might know that every Arduino board needs a way to be connected to a power source. The Arduino Uno can be powered from a USB cable coming from your computer or a wall power supply that is terminated in a power jack. In the picture bar, the USB connection is level 1 and the power jack is level 2. The USB connection is also how you will load code onto your Arduino board. So, a quick note is that do not use a power supplier greater than 20 volts as you will overpower, and thereby destroy your Arduino. The recommended voltage for most Arduino models is between 6 and 12 volts. Alongside with power USB power jack, we have pins. We have 5 pin, 5 volts away, 3.3 volt, GND analog jitter, PWM, and RF. The pins on your Arduino are the places where you connect wires to construct a circuit, probably in conjunction with a breadboard and some wire. They usually have black plastic headers that allows you to just plug a wire right into the board. The Arduino has several different kinds of pins, each of which is a label on the board and used for different functions. The GND. The GND is short for ground. There are several GND pins on the Arduino, any of which can be used to ground your circuit. The second thing is that we have 5 volts, which is a level 4, and 3.3 volt, which is level 5. As you might guess, the 5 volt pin supplies 5 volts of power, and the 3.3 volt pin supplies 3.3 volts of power. Most of the simple components used with the Arduino run happily of 5 volts or 3.3 volts. The analog pins. label 6. The area of pins under the analog label E0 through A5 on the Uno are analog pins. This pin can read the signal from analog sensors like temperature sensor and convert it into a digital value that we can read. The digital pin, you may notice that across from the analog pins are the digital pins which go from 0 through 13 on the Arduino. These pins can be used for both digital input, like telling if a function is pushed, so if a button is pushed, and digital output, like powering an LED. The PWM, uh, you may have noticed that the title next to the sum of the digital pins uh, 3, 5, 6, 9, 10, and 11 of the UNO. These pins act as normal digital pins, but can also be used for something called pulse width modulation, PWM, pulse width modulation. The RI function, the RI stands for analog reference. Most of the time, you can leave this pin alone. It is sometimes used to set an external reference voltage between 0 volts and 5 volts as the upper limit for the analog input pins. The third thing is reset button. Just like the original Nintendo, the Arduino has a reset button, which is labeled 10. Pushing it will temporarily connect the reset pin to ground and restart any code that is loaded on the Arduino. This can be very useful if your code doesn't repeat, but you want to test it multiple times. Unlike the original Nintendo, however, blowing on the Arduino doesn't usually fix any problem. The next thing is the power LED indicator. Just beneath and to the right of the word Uno on your circuit board, there is a tiny LED next to the word on. Label 11. This LED should light up whenever you plug your Arduino into a power source. If this light doesn't turn on, there is a good chance something is wrong. Time to check, time to recheck, sorry, time to recheck your circuits. The TX and RX LEDs. TX is short for transmit and RS is short for receive. These marking appear quite a bit in electronics to indicate the pins responsible for serial communication. In our case, there are two places on the Arduino Uno where TX and RX appear. Once by digital pins 0 and 1, and the second time next to the TX and RX indicator LEDs. These LEDs will give us notice, sorry, these LEDs will give us some nice visual indications whenever our Arduino is receiving or transmitting data, like when we are loading a new program onto the board. The main IC, level 13, the black thing with all the metal legs in an IC or integrated circuit, level 13, uh, think of us the brains Uh, think of it as the brains of our Arduino. The main IC on the Arduino is slightly different from board type to board type, but is usually from the Artemega line of ICs from the Atmel company. This can be important as you may need to know the IC type along with your board type before loading up a new program from the Arduino software. This information can usually be found in writing on the top side of the IC. If you want to know more about the difference between various ICs, reading the data sheets is often a good idea. The last thing that we're gonna talk about is voltage regulator, which is labeled 14. The voltage regulator is not actually something you can or you should interact with on the Arduino. But it is potentially useful to know that it is there and what it is for. The voltage regulator does exactly what it says. It controls the amount of voltage that is let into the Arduino board. Think of it as a kind of gatekeeper. It will turn away an extra voltage that might harm the circuit. Of course, it has a limit, so don't hook up your Arduino to anything greater than 20 volts. After talking about the Arduino, the input outputs, we're going to talk about more on analog pins and digital pins. So, an analog signal is generally bound to a range. In Arduino, that range is called 0 to 5 volt or 0 to 3.3 volt. If, for example, uh, we use a potentiometer, which is an analog component used to change the resistance of a circuit, we can manually adjust this range from 0 to 5 volt. In a program, this is represented in a range of 0 to 123, which is a 10-bit resolution. If we want an analog signal using pulse with modulation, PWM, we can use a range between 0 to 255 as we are using an 8-bit resolution. The, the digital pins. Uh, Notice that all communication between electronic components are facilitated by electronic signals. There are two main types of electronic signals, the analog and digital. A digital signal works as a bit different, representing only two binary states, 0 or 1, that are read as high or low states in the program. This is the most common signal type in modern technology. You can easily read and write digital signals are on an Arduino, which is useful to, for example, read part of states or to turn something on or off. Our digital signals might seem very basic, just 0 or 1, but are actually way more advanced. For example, we can create a sequence by sending a high or low state rapidly a number of times. This is known as binary sequence or bit stream. Now, let's talk about one of the most common components uh, in the world, LEDs. We can find LEDs everywhere today is in our lives. We can find them in our hours. We can find also them in our TV in our remote controller or TV remote controller. We can find them in buildings. We can also find them in aviation, aeronautic, robotics, and also to when we build a satellite. They are everywhere on Christmas Day, holidays, on vacations, or for special days. There are lifesaver as humanities, cars or bus use them, and also police and ambulance use them to send signal to population or to signal or to let people to know their position or that they are there in our place or around us. They are also uh, the app has to know if the the light rod is red or is red or it is green, and also to indicate us which direction to take. They also help us to grow efficiently our plants and and to maintain a certain type of photo in agriculture. They are also useful there. Also in the exit or in a building. So notice that LEDs come in a varieties of shapes and size. You will learn about those and how they work before diving into LEDs, the importance of current limiting resistors, and how to use them. So, what are LEDs? LEDs stand for light emitting diodes. It is one of the most common electrical components in the world, and it is a type of diode. The advantages of LED is that it is good for lower energy consumption. They have longer lifetimes. They improved physical robustness. They are at smaller size and they are faster switching. For example, when using a car, when you push your foot, uh, people around you could have the information more quickly than if you were using another type of signal. So, what are diodes? A diode is a semiconductor device. It conducts current in only one direction. It has two legs and it's polarized. This means that it have it does have the plus pole and the minus pole, and it allows current to flow in the circuit. So, how LEDs look like in a circuit? As you can see there, an LED in a circuit is powered in a circuit. Is this here? Sorry, here you have sorry a battery circuit where we can use an LED. So the current supplier is the battery or something else, and the LED is associated with a resistor to 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 make our circuit work correctly in order to not fire our LED. So in real life, the LED look like the one on the right left in the right hands of our in the right hand. So as I told you, diodes are polarized. This means that LEDs are also polarized with the long leg, which is the anode, which is the plus pole, and the short leg, which is the cathode, which is the small leg of our LED. And in the circuit, LEDs looks like. Notice that in the in notice that a flow current flow from the anode, which is the long leg, to the cathode. And if you want to reverse the process, you're going to, your LED will not be powered at all. So, how LEDs look like, and what is the anatomy of an LED? So, this figure illustrates the internal structure and external identification of a standard through-hole LED package, explaining how the electrical and optical paths are arranged to produce visible light. The outer transparent body is the epoxy lens or case which protects the internal components and also act as an optical lens to focus and direct the emitted light outward. The shape of this epoxy case helps control the viewing angle and light intensity distribution. Inside the epoxy case is the semiconductor die, which is the actual LED chip where light is generated. This die is made of a p-n junction semiconductor material and is mounted in a reflective cavity. The reflective cavity surrounds the die and reflects light that is emitted downward or sideways back toward the top of the LED, increasing overall light output and efficiency. The semiconductor die is electrically connected using a wire bond, which is a very thin metal wire that connects the top of the die to one of the metal support. This wire bond provides the electrical connection to the anode side of the LED. The die itself is mounted on a metal support called the anvil, which also reverse as a heat sink and provides the electrical connection to the cathode. The anvil on the post together for the lead frame, which is the internal metal structure that supports the die and connects it to the external leads. Externally, uh, the LED has two leads that allow it to be connected into a circuit. The anode, as I told you previously, which is the positive terminal, is identified as the long lead, while the cathode, which is the negative terminal, is the short lead. Additionally, a flat spot on the epoxy case is used as a visual indicator to identify the cathode side, help ensure a correct polarity when installing the LED. In operation, when a forward voltage is applied with, with the anode connected to the positive supply and the cathode to the negative supply, current flows through the lead frame into the semiconductor die and out through the wire bond and environment. Inside the die, electrons can electrons. Sorry, let me come again. Uh, Inside the die, electrons and holes will combine and emit light, which is reflected by the reflective cavity and guided outward by the epoxy lens. This combination of electrical connections, mechanical support, and optical shaping allows the LED to efficiently convert electrical energy into visible light while remaining compact and robust. So let's move on how and what our PN junction works. So an LED or light emitting diode, sorry, is a semiconductor device based on a PN junction that emits light when it is forward biased. The structure consists of two doped regions, the p-type region, which contains a high concentration of holes, and the n-type region, which contains a high concentration of free electrons. When no voltage is applied, the junction forms an internal potential barrier that prevents charge carriers from crossing. When a battery is connected so that the positive terminal is connected to the p type and the negative terminal to the n type, the LEDs is forward biased. This applied voltage lowers the potential barrier at the junction and allows charge carriers to move. Under forward bias, electrons in the n type region are pushed toward the junction while holes in the p-type junction region move in the opposite direction, also toward the junction. This carrier movement constitutes an electric current through the device. Near the junction, near the junction, uh, electrons and holes meet and interact. This interaction is called recombination. During a recombination, an electron from the conduction band of the n-type material face the hole in the valence band of the p-type material. To understand this process energetically, the bond diagram is used. The, the diagram shows uh, the diagram shows the conduction bond, the valence bond, and the band gap forbidden bond between them. The Fermi level represents the energy level that indicates the probability of electron occupancy. When the LED is forward biased, electrons get enough energy to move into the conduction band and cross the junction. When an electron combines with a hole, it drops from the conduction band to the valence band, crossing the band gap. The energy difference between these two bands is released as a photon, which is entitled as light. The emitted light is represented in the diagram as a wave, indicating electromagnetic radiation. The energy of the photon and therefore the color wavelength of the light is directly determined by the size of the band gap of a semiconductor material. A larger band gap produces high energy photons, blue or ultraviolet light, while a smaller band gap produces lower energy photons, red or infrared light. Because LEDs use direct band gap materials, most of the energy released during recombination is emitted as light rather than being lost as heat. So, in summary, when a forward voltage is applied to an LED, electrons and holes are injected into the junction. We combine in the active region and release energy as light due to transitions across the band gap between the conduction band and the valence band. This continuous process of carrier injection and recombination results uh, in steady light emission, which is the fundamental operating principle of an LED. The next step to understand an LED is to understand how current flows, how current flows in a circuit. How current flows in a circuit. And it's important to notice all the changes that occur in our circuit. So please, we are we have the breakdown region, the reverse region, and the forward region. Those regions are very important for the LED. So the figure represents the current voltage, a characteristic of a dot, showing how the dot behaves on the forward bias, reverse bias, and breakdown conditions. The horizontal axis represents the voltage, the applied cross without. When we talk about that, please remember that remember that an LED is also a type of diode of dot. Sorry. So while the vertical axis represents the current flowing through it, the polarity convention is indicated by the dot symbol, where the voltage V is defined with the positive terminal on the anode side and the negative terminal on the cathode side, and the current I is defined flowing from anode to cathode. In the forward region, where the applied voltage is positive, the dot is forward biased. For small forward voltages, the current remains very small because the internal potential barrier of the PN junction has not yet been sufficiently reduced. As the voltage increases and reaches the dot forward voltage of the VT, the barrier is effectively overcome and the dot begins to conduct so strongly. Beyond this point, a small increase in voltage causes a rapid nonlinear increase in current, which is shown by uh, the steep rise of the curve. This region corresponds to normal dot operation, where the dot allows current to flow easily in the forward direction. In the reverse region, the applied voltage is negative and the dot is reverse biased. In this region, the dot blocks a current flow and only a very small reverse leakage current flows due to minority carriers. This current is nearly constant and remains close to zero over a wide range of reverse voltages, as shown by the almost flat portion of the curve in the reverse region. As the reverse voltage continues to increase in magnitude, the dot eventually reaches the breakdown region at the breakdown voltage VBR. At this point, the electric field across the junction becomes strong enough to cause a sudden and large increase in reverse current. This sharp rise in current is shown by the steep curve in the breakdown region. In ordinary doubts, operation and breakdown can damage the device, while in, while in a specially designed doubt such as Zener doubts, breakdown is used intentionally for voltage regulation. So to sum up, in summary, the doubt IV characteristic shows that the doubt conducts significant current only in the forward direction after the forward voltage VD, sorry, the forward voltage VD is which blocks current in the reverse direction under normal conditions. and conductively in reverse on the breakdown voltage, the VBR, is exceeded. This asymmetric behavior is the fundamental electrical property that allows the diode or an LED to act as one-way current device. Now, let's talk about another component, a resistor. A resistor are one of the most common and important electrical components in digital circuits. So resistor, as its name indicates, resist the flow of charge or current in a circuit. Resistors have no polarity, so you can put them into a circuit in either orientation. Resistors have two characteristics, ohms and watts. So resistor is an insulator uh, in opposed to opposite to conductor. A conductor lets current to flow easily. To flow conductor sorry lets current to flow easily rather than with insulators that is opposed to current to flow efficiently. So as you may notice, to make a resistor with a specific resistance R, component manufacturers carefully select the type, amount, and shape of a resistive material and embed it into insulated packaging. In the image below, for example, a resistive material like carbon is wrapped around an insulator and covered by a thin insulating material. The more wraps, the higher resistance. And this should uh, intuitively make sense. Increasing the number of wraps simply increases the length of the resistive material or the amount of resistive material electrons have to navigate through. And there are three ways to read resistor. You keep them arranged in package or to learn how to decode the color code bands or use a multimeter on the red resistance setting. For example, when you buy when you when you buy when you buy a set when you buy a resistor, you have some type of data sheets or some types of paper that indicates you how to read a resistor. Let's take an example. Imagine that we have a resistor like this, what we have, and we want to read the value of that resistor. How to do? You read the value from the left hand to the right hand, and the value is expressed in ohm. For example, here we have the blue, so we have green, blue, and orange. But the green, when we see the color in the data sheet, the first color of green is correspond to 5. So we put 5 here. The second color, the blue, is uh is 6. So we put 6. And the final value, orange, is how times we multiply the two first value. For example, here the third digit, the third color here is is orange. So we multiply the two first value by 100, sorry, by 1,000, and this gives us uh, the the value of the resistor. Here you have, for example, 56 kilo ohm plus minus 5%. The 5% comes from the last color, which is here the gold band. The gold band. We can do the same with a with a resistor which is in person. Okay, we can also um we can also keep in mind sometimes people have I think of some baby world where British very good wife. We have the second song which is bad boys. Our young girls are violet generally wins. I'm not a good singer, but you can find those songs in internet. So, as you may notice, we don't use uh, an LED isolated. As we don't know, we use both resistor and LED batteries integrated in a circuit, and this circuit is register is this circuit is and into this circuit we have someone who has observed something and put down a law which is the Ohm's law. Ohm's say that the current is equal to the voltage divided by the resistor. And in daily life, how to represent um, the power supplier? We have different type of power supplier and how to represent sorry a resistor like this. Also how circuit look like in daily life, etc., etc. But when you are building a circuit or and when you are designing or when you are drawing a circuit at home, there are many ways to say that there is a node here, there is no connection here, there is connection here. So there's many types or many ways how to say that there are connection in your circuit. Same as when you want to represent a ground or when you want to represent a current supplier, a voltage supplier. The same things here. So generally, this is how circuit look like in real life. It is difficult to read them if you are not if you have not a great background in electronics or something else. So this is the end of our tutorial, and I want to thank you very much. So see you for the next tutorial. Now that we're going to go deeper on we are going to make a lot of practice instead of a lot of speech. No, we leave place to practice, and see you next for the next video. Thank you.